Alcohols and phenols consist of two main parts: an alkyl or aryl group and a hydroxyl group. The hydroxyl group chiefly determines the physical properties of the alcohols and phenols. The nature of the alkyl or aryl group does modify these properties to some extent. The boiling points of both alcohols and phenols increase as the length of the carbon chain increases, as shown in the table here for some primary alcohols. This is due to increasingly strong London forces as the length of the carbon chains increase. What is the effect of branching on the boiling point of alcohols? Use the information in the table. The table shows 3 butanol isomers, which all have the same molecular formula. As the branching of the carbon chain increases, the molecules attain a spherical shape and the surface area decreases. As a result, the van der Waals forces of attraction become weaker, and therefore the boiling point decreases with an increase in branching. Therefore, among the isomers of butanol, tertiary butyl alcohol 2-methyl-propan-2-ol has the lowest boiling point, as shown in the table. Alcohols and phenols have boiling points higher than other classes of organic molecules, such as hydrocarbons, ethers, haloalkanes, and haloarenes, with similar molecular masses. For example, the boiling point of ethanol is considerably higher than that of methoxymethane or propane, although all the 3 substances have very similar molecular masses. Both alcohols and phenols can participate in intermolecular hydrogen bonds due to the presence of the polar hydroxyl group. Thus, alcohols and phenols have higher boiling points than ethers or hydrocarbons, which cannot participate in hydrogen bonding. Alcohols and phenol can both form hydrogen bonds with water, and so both are water-soluble. The solubility of substituted phenols is very low in comparison to phenol. It should be noted, however, that as the alkyl or aryl groups get larger, the solubility decreases. Ethanol and other low molecular mass alcohols are completely miscible in water. They can dissolve in water in any proportion. Let's apply our knowledge to answer some questions. Which of these molecules would you expect to have the higher boiling point? It's helpful to draw structures for these types of problems. Essentially, you need to determine which molecule in each pair has the stronger intermolecular attraction. For set A, 1-heptanol has the higher boiling point because it has the longer carbon chain. For set B, 1-propanol has the higher boiling point. 1-propanol with its hydroxyl group can participate in intermolecular hydrogen bonds, while the ether methoxymethane cannot. For set C, 1-hexanol has the higher boiling point. Its carbon chain is unbranched, giving it stronger London forces than the branched chain in its structural isomer 2,3-dimethylbutane-1-ol. We'll start with the term nucleophile. The word nucleophile means nucleus seeking. In other words, A nucleophile typically has a lone pair of electrons or negative charge that it can use to make a covalent bond. A nucleophile can be described as a Lewis base or an electron pair donor. The chloride ion shown here is an example of a nucleophile. Another important term is electrophile. The term means electron seeking. An electrophile typically has a positive charge and an empty orbital. Electrophiles are Lewis acids or electron pair acceptors. The cations shown here are both examples of electrophiles. Alcohols are a versatile class of compounds. They can act as nucleophiles or as Lewis bases. Note the lone pairs on oxygen in the alcohol formula. When alcohols act as nucleophiles, the bond between the oxygen and the hydrogen is broken. Protonated alcohols act as electrophiles. Electrophiles will react with electron-rich species such as nucleophiles. In the reaction shown here, the nucleophile chloride ion attacks carbon. The bond between the C and the O breaks in the alcohol as the products form. Essentially, we can separate the reactions of alcohols in two major classes. Reactions involving cleavage of the oxygen-hydrogen bond, which occur for both alcohols and phenols, and reactions involving cleavage of the carbon-oxygen bond. Only alcohols undergo reactions that break the carbon-oxygen bond. We'll start with the reactions that involve the cleavage of the oxygen-hydrogen bond in alcohols and phenols. Alcohols and phenols react with active metals, such as sodium, potassium, and aluminium to form alkoxides or phenoxides and hydrogen. The general formula of the reaction is shown here. Notice that the OH bond breaks as the metal alkoxide forms. Try to solve this problem on your own before checking the answer. Write the chemical equation for the reaction of propan-1-ol with potassium. A reaction between an alcohol and potassium metal will form a potassium alkoxide. In this case, potassium propoxide forms as shown here. Phenols react with aqueous sodium hydroxide to form sodium phenoxides. Water is a byproduct of the reaction. Note that alcohols do not react with aqueous sodium hydroxide because they do not have enough acidity. The reactions we just studied illustrate that alcohols and phenols are acidic compounds. Phenols are comparatively more acidic than alcohols. They are Bronsted acids or proton donors. As the equation here shows, they can donate a proton to a stronger base. Alcohols can donate protons because the oxygen-hydrogen bond is polar. Since oxygen is more electronegative, it has a partial negative charge. The hydrogen has a partial positive charge. Let us now understand why primary alcohols are more acidic than secondary alcohols, which in turn are more acidic than tertiary alcohols. The presence of alkyl groups in alcohols increase the electron density around oxygen by the inductive effect. As alkyl groups donate electron density to the oxygen-hydrogen bond becomes less polar. It then becomes difficult to remove an H+ ion from the alcohol. The inductive effect explains the relative acidities of alcohols. Methyl and primary alcohols, which have the lowest degree of the inductive effect, are slightly more acidic than secondary alcohols. Secondary alcohols are slightly more acidic than tertiary alcohols, which have a strong inductive effect. Alcohols are weaker acids than water. We know this because alkoxide ions react with water to form the alcohol, the conjugate acid, and a hydroxide ion. Since this reaction favors the products, it means that water is a better proton donor than the alcohol. Versatile alcohols can also act as Bronsted bases or proton acceptors. The reaction here shows an alcohol accepting a hydrogen ion or proton from HCl. Phenols are also acidic in nature. Note that the benzene ring acts as an electron withdrawing group. The resonance structures of phenol, shown here, illustrate that the oxygen atom in phenol has a partial positive character. Phenols are Bronsted acids or proton donors. In fact, phenols are stronger acids than water or alcohols. The presence of the aromatic ring leaves less electron density on oxygen. So, the oxygen-hydrogen bond is more polar. This makes the loss of a hydrogen ion more favorable. The phenoxide ion forms when phenol ionizes by losing a hydrogen ion. The resonance structure of the phenoxide ion are shown here. Notice that the negative charge of the ion is delocalized, which stabilizes the ion. On the other hand, in the alkoxide ion, the negative charge is localized on oxygen, which makes it less stable. The charge delocalization favors the ionization of phenol. Note that, in phenol, the charge separation in the resonating structures makes it less stable than the phenoxide ion. Hence, phenols lose a hydrogen ion more readily than alcohols. In other words, phenol is a stronger acid than alcohols. We can also discuss acid strength by comparing acid dissociation constants, or Ka. Strong acids have large acid dissociation constants. pKa values are also used to compare acid strengths. The pKa of any acid dissociation constant is defined as the negative log of the Ka value. Since pKa is a logarithmic function, as the Ka increases, as acid strength increases, the pKa value decreases. Therefore, a higher pKa value corresponds to a weaker acid. Try to reason this problem out on your own. Which one would you expect to have the higher pKa value? Ethanol or phenol? How should their pKa values compare to water? You have learned that phenols are stronger acids than alcohols and water. You also know that water is a stronger acid than ethanol. Finally, you learned that stronger acids have lower pKa values than weaker acids. So, phenol should have a lower pKa than water and ethanol. water should have a lower pKa than ethanol. You can confirm your reasoning by comparing the actual pKa values. As expected, phenol has the lowest pKa and ethanol the highest. Substitutions on the benzene ring of phenol can alter phenol acidity. The presence of electron withdrawing groups, such as the nitro group, make phenols more acidic. This is especially true when the electron withdrawing groups are in either the ortho or para positions. In these positions, nitro groups allow for resonance structures that stabilizes the phenoxide ion by allowing more delocalization of negative charge. Conversely, the presence of electron-releasing groups, such as alkyl groups on the benzene ring, result in weaker acids for substituted phenols. For example, compare the pKa values of phenol and cresol. Phenol has a lower pKa value than cresol, reflecting that phenol is the stronger acid of the two. Remember that pKa values use a logarithmic scale. It's time to turn our attention back to reactions of alcohols and phenols. One important class of reactions is called esterification. Both alcohols and phenols react with carboxylic acids to form esters and water. This reaction is slow and reversible. Sulfuric acid is used as the catalyst in this reaction. Alcohols and phenols can also react with acid chlorides to form esters. These reactions are carried out in the presence of a base, such as pyridine. The base neutralizes the hydrochloric acid as it forms, which causes the equilibrium to shift right. Additionally, alcohols and phenols can react with carboxylic acid anhydrides to form an ester as well as a carboxylic acid. These reactions are slow and require heating. Try to work out this problem on your own before continuing. Write the structure of the primary product formed when benzoic acid and N-propanol are combined in the presence of sulfuric acid. Start by drawing out the structures of the reactants. You should recognize this as an esterification reaction. Propyl benzoate is the main product of the reaction. One application of esterification is the synthesis of aspirin. Acetylation is the introduction of an acetyl group into alcohols and phenols. When salicylic acid, a carboxylic acid, is mixed with ethanoic anhydride, a carboxylic acid anhydride, acetyl salicylic acid, or aspirin is the primary product. Acetic acid or ethanoic acid is also formed. Now let's turn our attention to reactions that result in cleavage of the carbon-oxygen bond. Only alcohols show these types of reactions. Alcohols react with hydrogen halides to form alkyl halides and water. The Lucas test for alcohols uses the Lucas reagent, a solution of zinc chloride in concentrated hydrochloric acid. When the insoluble chloroalkane forms, the resulting mixture has a cloudy, turbid appearance. The Lucas test is used to differentiate between primary, secondary, and tertiary alcohols. An alcohol, zinc chloride, and hydrochloric acid are combined at room temperature. A primary alcohol leads to no visible change in the mixture. A secondary alcohol will show cloudiness in about 3 to 5 minutes. A tertiary alcohol turns cloudy almost immediately. Alcohols react with phosphorus tribromides to form alkyl bromides. A general equation is shown here. The phosphorus acid that forms is water-soluble and can be washed away. Another important reaction of alcohols is acid-catalyzed dehydration. You can think of these reactions as the removal of H2O from the alcohol. The alcohol must be treated with a protic acid, which acts as a catalyst for the formation of an alkene. Acid-catalyzed dehydration of primary alcohols requires the use of sulfuric acid. Secondary and tertiary alcohols can be dehydrated under milder conditions using phosphoric acid as a catalyst. In general, primary alcohols are the least reactive, while tertiary alcohols the most reactive towards acid-catalyzed dehydration. Here is a problem for you to try. Draw the structure of the major product formed when 2-methyl-2-propanol is heated with sulfuric acid. You should recognize these conditions as acid-catalyzed dehydration of an alcohol. Start with the structure of the reactant. Remove the OH group and an H from any of the 3 surrounding carbons. They are all equivalent in this molecule. It is very important to understand the mechanism involved in acid-catalyzed dehydration of alcohols. The proposed mechanism takes place in 3 steps. Step 1 involves the formation of a protonated alcohol or an alkyl oxonium ion called tertiary butyl oxonium ion. This step is a fast equilibrium. The second step of the mechanism is the dissociation of the alkyl oxonium ion to form a carbocation, that is tertiary butyl carbocation. This is the slow step or the rate-determining step of the mechanism. The final step of the mechanism eliminates a proton from the carbocation to form an alkene 2-methyl-1-propene. Notice that the hydrogen ion used in the first step of the mechanism is regenerated in this step. This is consistent with acid catalysis. To drive the equilibrium to the right, the alkene is removed as it is produced. Alcohols can also undergo oxidation to form compounds with carbon-oxygen double bonds. These are also sometimes called dehydrogenation reactions, as they involve the loss of hydrogen molecule from the reactant. Notice that the oxygen-hydrogen bond breaks as well as a carbon-hydrogen bond. Depending on the oxidizing agent used, primary alcohols may be converted into aldehydes and ultimately into carboxylic acids. Let's consider the different reaction conditions and their outcomes. When a primary alcohol is treated with acidified potassium permanganate, a very strong oxidizing agent, the alcohol will be converted directly into a carboxylic acid. Chromium 6 oxide or chromic anhydride is another strong oxidizing agent. In anhydrous conditions, it can be used to convert primary alcohols into aldehydes. However, chromic anhydride is highly toxic and environmentally hazardous. An alternative route to the preparation of aldehydes from primary alcohols is to use pyridinium chlorochromate, or PCC. The addition of PCC to a primary alcohol will produce an aldehyde. PCC is also toxic. What reagent would you use to carry out the oxidation of 1-propanol to form 1-propanal? From the structures, we see that this reaction converts a primary alcohol into an aldehyde. Therefore, we don't want to use potassium permanganate, which would make a carboxylic acid. We can use either PCC or chromic anhydride to carry out this reaction. Treating secondary alcohols with chromic anhydride will produce ketones. Try to answer this question independently before checking the answer. Write a balanced equation showing the structure of the primary organic product formed when 2-butanol is treated with chromic anhydride. 2-butanol is a secondary alcohol. Chromic anhydride oxidizes secondary alcohols to form ketones. The product is 2-butanone. Tertiary alcohols don't undergo oxidation reactions. Under strong conditions, that is, using strong oxidizing agents at elevated temperatures, cleavage of carbon-carbon bonds is observed. A mixture of carboxylic acids results. Dehydrogenation reactions of primary or secondary alcohols can also be carried out by passing vapors of the alcohols over heated copper. Under these conditions, primary alcohols form aldehydes, while secondary alcohols form ketones. If vapors of tertiary alcohols are passed over heated copper, dehydration reaction takes place to form alkenes. For example, 2-methyl-2-propanol forms 2-methyl-1-propene when passed over heated copper. As the alkene forms, the OH group and one hydrogen from an alkyl carbon are lost to create a water molecule.